Welcome back. In this session, I am teaching Chapter 4, RAG Knowledge Base. RAG, or Retrieval Augmented Generation, is a method where the system first searches trusted data sources and then uses that retrieved content to create the final response. Instead of relying only on model memory, it grounds answers in current, business-specific information like policies, pricing, and product details. The flow is simple. User query comes in, relevant knowledge is retrieved, that context is added to the prompt, and the model generates an answer. This improves accuracy, reduces guesswork, and helps the agent stay aligned with what your organization has officially documented. In short, retrieve first, then generate, so responses are both useful and reliable. Our objective is to ground agent responses using company data, with semantic retrieval using embeddings, and a deterministic fallback when needed. In this chapter, we are not generating long LLM replies yet. We are building retrieval, scoring, and escalation in a reliable pipeline. In this chapter, we will mainly use 4 files: app.py, AgentDesk_AI/rag.py, AgentDesk_AI/tools.py, and data/company_knowledge_base.json. Company_knowledge_base.json stores our business knowledge entries. Each entry has a clear title and content, so the agent can retrieve the right information for a customer query. This file works as the source of truth for pricing, integrations, activation support, and demo guidance, helping responses stay accurate and grounded. RAG.py is the retrieval engine for this chapter. It reads company_knowledge_base.json, converts both the user query and knowledge entries into embeddings, and compares them using Cosine similarity. Then it ranks results and returns the top matching documents as grounded context for the agent response. Tools.py exposes 3 tools: knowledge search, lead scoring, and escalation decision. App.py runs the terminal loop and prints structured output. So the flow is terminal input in app.py, orchestration in agent.py, tools execution in tools.py, and semantic retrieval from rag.py. Now I will run Chapter 4. I will move into Chapter 4. I will type cd chapter_04_rag_knowledge_base. Now I will run the app. I will type python app.py. Expected behavior. Retrieval should return top KB hits like pricing and integrations. Lead score starts at 3, then adds 3 because pricing intent is present, so score should be 6. Escalation should remain false because no escalation keyword is present. Now I will test the second message. I paid but not activated, and this is frustrating. Expected behavior. Retrieval should strongly match activation support. Escalation should be true because words like paid and frustrating are in escalation keywords. Lead score may remain near base unless commercial words appear. Now I will test the third message. Book a demo for my business. Expected behavior. Retrieval should include demo booking. Lead score should increase because demo and business are commercial signals. Escalation remains false. Now I will stop the app. Exit. Now let us understand what happens behind the scenes. App.py handles input-output only. For each message it calls build_agent_response. Inside agent.py, the pipeline is deterministic. First, search_knowledge_base open parenthesis, customer_message close parenthesis. Second, score_lead open parenthesis, customer_message close parenthesis. Third, decide underscore escalation open parenthesis customer underscore message close parenthesis. Then it builds JSON with fixed fields, intent, lead underscore score, customer underscore reply, internal underscore summary, should underscore escalate, escalation underscore reason, and next underscore action. Intent is fixed as KB underscore grounded underscore response in this chapter. Now let us understand rag.py, because this is the core of chapter 4. Load underscore knowledge underscore base reads data slash company underscore knowledge underscore base dot JSON. Underscore embed underscore texts calls open AI embeddings using model from embedding underscore model default text dash embedding dash 3 dash small. The code embeds both query and KB documents. Then cosine similarity measures closeness between vectors. Simple underscore rag underscore search open parenthesis query comma top underscore k equals 2 close parenthesis sorts by similarity and returns top 2 matching docs. This is semantic retrieval, not just plain keyword matching. Important reliability detail. If the embedding call fails, or OpenAI underscore API underscore key is missing, the code enters fallback mode. Fallback uses underscore keyword underscore fallback, which counts query word overlap with each document and returns top results deterministically. So students can still run this chapter offline or without an API key and still observe retrieval behavior. If you want to run actual embeddings, go to your OpenAI developer account, create an API key, add it in the .env file as OpenAI underscore API underscore key, and run this chapter again. For OpenAI underscore API underscore key setup details, refer to Chapter 4 readme.md. For now, we are not entering any key and will depend on fallback for training purpose. It still returns RAG-like behavior, and you can observe the result. Now check tools.py. Search underscore knowledge underscore base calls. Simple underscore rag underscore search. Score underscore lead starts at 3 and adds 3 if message contains pricing, demo, buy, or business. Max score is capped at 10. Decide underscore escalation returns true if message contains paid, refund, legal, frustrating, angry, or cancel. This keeps control points simple and testable. Now let us summarize Chapter 4. We connected a company knowledge base to semantic retrieval. We ranked relevant entries using embeddings and cosine similarity. We preserved deterministic behavior with a keyword fallback. We combined retrieval with lead score and escalation checks into one structured response. This chapter prepares us for next chapter where these tools are exposed through an MCP server for external agent clients.